Hi everyone. So welcome to your lesson on exponential application problems. So our goal for today is that you're going to solve various different types of application problems using what you've learned about exponents and exponential functions. So essentially we're going to go through two different types of word problems. First, we're going to determine if a situation is linear or exponential. So essentially, we're going to give you like a word problem, and you're going to have to use the information that we give you to tell us if that situation is linear, exponential growth, or exponential decay. And then we're going to find the area of a rectangle using our rules of exponents. So let's get started. So example letter A, determine whether the relationship can best be described as linear, exponential growth, or exponential decay. So your parents originally bought your computer for $3,000. Every year it loses value. After 1 year of owning the computer, the value of the computer is $2,400. After 2 years, it's valued at $1,920. So what you can kind of do is make like a little table. Like this, and say we want to look at the value of your computer and the number of years that have gone by. So you originally bought the computer for $3,000, right? And so essentially the number of years, that's when we first bought it. So that's at the start, which is at year 0. A year later, it's now worth $2,400. And then after 2 years, it's worth $1,920, right? So remember what we learned about linear functions? Linear functions, when you look at the y values of a linear function, they're going to either add or subtract by a constant. So the value of the computer is going down, right? It's decreasing. We start at $3,000, we go down to $2,400, and then $1,920. So in other words, can we subtract the same number every time to get the next value? So if we look at this, we can say, well, 3,000 minus 2,400 is 600. So that means that if I start at $3,000 and subtract 600, I would get to this number here, right? Now, if I can now take $2,400 and subtract 600 again and get to that, then that tells me that this would be a linear relationship. But 2,400 minus 600 is 1,800, right? It's not 1,920. So that tells me that this is not linear. I can't add or subtract a constant every time to get the next value. So instead, we're going to check to see if it's exponential. Okay, and if a function is exponential growth or decay, we're either going to multiply or divide by the same number or a constant every time. All right, so how do you check that? Well, here's what you're going to do. Essentially, what you're going to say is you want to be able to, the easiest way to think of it is we want to be able to take $3,000 and multiply by a number to get this, and then multiply by that same number to get this, right? Well, the opposite of multiplication is division. So if we can take 2,400 and divide by 3,000, get out your calculator, do that real fast, but you're going to get 0.8. So now the question is, if I take the next number, if I take $1,920 and I divide by 2,400, use your calculator and check that real fast. But you're going to get 0.8 again. So notice, because we get this same number here, that tells us that this function is exponential. In other words, I can kind of fill in this question mark that I put there, and I can multiply by 0.8. So again, check on your calculator. I can take 3,000 and multiply it by 0.8, and I get $2,400. And then if I take $2,400 and multiply by 0.8 again, I'm going to get $1,920. So because that always works, I'm always multiplying, that tells me that this function is exponential. Or this situation, I should say, is exponential. Now, we have to decide if it's exponential growth or decay. So the value of your computer is going down. It's decreasing in value. So because it's decreasing in value, we're going to call this exponential decay. So that's how you would answer a question like this. This is kind of like, guess and check. You're going to be using the calculator to figure this out. But again, you want to find out, is the pattern one where you have to add or subtract a constant, or is it where you're always multiplying or dividing? Let's try a couple more examples. So example B, a cable company charges $44 per month for basic service. If you have one premium channel, the total bill is $60. If you have two premium channels, the bill is $76. So let's kind of get this down. Okay, so if we have no premium channels, 1 or 2. So if we have no premium channels, our bill is $44 a month, right? If we have one premium channel, our bill is $60 a month. And if we have two premium channels, our bill is $76 a month. So again, I'm going to look to see if it's linear first, if I can either add or subtract the same number every time, just because I think checking to see if it's linear is always easier to begin with. So I want to say, is there a number that I can add or subtract to this first number to get the second one? Well, 44 to 60, so I know obviously if it were linear, I'd be adding a number. So the opposite of adding is subtracting. So let me check. What's 60 minus 44? Use your calculator. It's 16, right? So I can take 44 plus 16 and get 60. Let's see if that same pattern holds. What is 76 minus 60? It's also 16, right? So I can take 60, add 16 again, and get 76. So because each time I'm adding 16, that tells me that this situation is linear. And so when you answer a question like this, your answer is either going to be the word linear, the word exponential growth, or exponential decay. And this table that I made and this kind of work that I have here in the blue, that's like my work. All right? Let's try another one. So on your 16th birthday, you deposit $500 in a savings account. When you turn 17, the account has a balance of $512.50. On your 18th birthday, the account has a balance of $525.31, okay? So let's make a little table with this information. All right, so when we turn 16, we're depositing $500, right? When we're 17, we have $512 $12.50. And then when we're 18, we have $525.31. So same thing as before. Is it linear exponential growth or exponential decay? So can I add or subtract a number every time to get the following number? So I'm going from 500 to 512 to 525, right? So obviously if it were linear, I'd be adding a number. So what can I add to 500 to get to the next number? So the opposite of addition, to try and like kind of figure that out, is subtraction. So $512.50 minus 500 is $12.50, right? Use your calculator if you need to. And then the next one, so I would add $12.50. So the next one, what can I add to this to get this? So I have to do $525.31 minus $512.50. So use your calculator. So here I get $12.81. So that's no good. These numbers don't match up. So I'm not adding the same number every time. So that tells me that this is not linear. This situation is not linear. So let's now check to see if it's exponential. If it were exponential, again, I would be able to multiply 500 times a number to get this, and then $512.50 times that same number to get this, right? So how do I figure out what that number is? The opposite of multiplication is division. So I can take $512.50 and divide by 500. And when I do that, I get 1.025. So in other words, and you can double check this, if I take 500 and multiply by 1.025, I'll get $512.50. So now let's see if I take $525.31 and divide by 512.50. Use your calculator. So you're going to get 1.024995, right? But when I round that, I get 1.025. So they round to be the same number. So, and again, use your calculator, 1.025. Use your calculator to check. Multiply $512.50 times 1.025. And you'll get this number here, this $525.31. So because I'm always multiplying by the same number, that tells me that this is exponential. Now, is it growth or decay? The amounts are getting bigger, right? We start at $500, we go to $512.50, $525, right? So this is exponential growth. Okay? So now you saw an example of exponential decay, what that would look like. Then you saw an example of a linear situation. And now here, the one we just did was an example of what exponential growth would look like. So now I want you to take a minute, pause the video here, and here's 5 problems that I want you to try. So try these problems, write down your work, go through this, pause the video, and then when you unpause, you'll come back and see the answers. You can check your work. All right, guys, welcome back. Hopefully you worked on these problems. I'm going to give you answers now. Please check your answers. So 1 should be exponential growth, because hopefully you found that every year the tuition was multiplied by 1.07. Number 2 is linear, because for every additional page, we're adding 6 seconds to the time. Number 3 is exponential decay, because every year we can get the attendance by multiplying by 0.945. Number 4 is exponential growth, because every year we can multiply Chad's GPA by 1.25. And then number 5 is a weird one. It's not linear, because if we go from 7 to 6.9%, we're decreasing. We would subtract 0.1%. But then to go from 6.9 to 6.7, we would subtract 0.2%, right? So it's not linear. And it's also not exponential, because if I divide 6.9 divided by 7, I get 0.986. And then if I divide 6.7 divided by 6.9, I get 0.971. So 0.986 and then 0.971 are close, but they're two different numbers. So therefore, this is not linear, and it's not exponential growth or exponential decay, and that's okay. That happens. Not every function is either linear exponential growth or exponential decay. All right, good job with those, guys. We're gonna kind of like switch gears, and let's try to find the area of a rectangle. All right, so hopefully you should be familiar with this. You found area of a rectangle before, right? So to find the area of a rectangle, we typically have this formula. Area is equal to either base times height, or some of you might say length times width. Whichever one, it doesn't matter. They both mean the same thing. But in this case, we would say that the area of this rectangle is equal to 14 times 5, which is 70 units squared. Now we say units squared. Hopefully you remember this from when you calculated area, because we don't know if this is like 5 inches, 5 centimeters, 5 feet. We don't know. So we can just write units squared. All right. So let's kind of take that knowledge and apply it to, well, what if I now have things like this, where I have these rectangles that have these sides that have variables in them, okay? So let's try a couple of these examples. We're going to find the area of each rectangle. So number 1, my length is x plus 8, and my width is 3, or base and height, however you want to think of it. But I still do this the same way. I would multiply the two together to find the area. So I'm going to multiply 3 times x plus 8. But notice I put the x plus 8 in parentheses, because I'm multiplying 3 times that whole thing. So I have to distribute this 3. So this ends up being 3x plus 24, right? But then I need units squared. So final answer, there you go. All right, number 2. Same idea. I'm just going to multiply the base times the height. So I have 2x times 3y squared. So when I multiply these together, 2 times 3 is 6. And my two variables are two different variables, so I have two different bases. So it's just going to be 6xy squared units squared. Makes sense? All right. So now here's a couple you try problems. Pause the video, and we want you to find the area of the rectangle. All right, so pause the video, find the area of the rectangle, and then when you unpause, you can check your answers. All right, welcome back. Hopefully you worked through these. and you found that the area of this one here is going to be 36 x to the 5th y to the 6th units squared. And then number 4 is going to be 10x to the 6th y to the 4th units squared, right? We're multiplying the base times the height, or the length times the width. And remember, when we multiply with exponents with like bases, we add the exponents. All right, so now we're gonna kind of like work backwards. So essentially, if you're given an area, here's my area, and the measurement of one side, there you go. How do you find the measurement of the missing side? That's that one. So if I know that area is equal to, let's say, base times height, right? And if I have this information that I underlined in blue here, let me fill in that information. The area is 40 centimeters squared. And I don't know what the base is. It was a question mark. But I know that the height is 8 centimeters, right? Now, instead of putting a question mark there, in math, we like to put like a variable. Let's call that x. So to find the measurement of the missing side, to solve for x, this means like x times 8 centimeters. I can divide both sides by 8 centimeters. That cancels that. And now I'm dividing. 40, which was the area, divided by 8 is 5. And actually, look, even though we're talking about centimeters, this isn't like a variable like we normally think of, like an x or a y, but I can use my rules of exponents. When I divide, I subtract the exponents. So 2 minus 1 is 1, so 5 centimeters. So that tells me that this missing side was 5 centimeters. And does that make sense? Well, I can check. 8 centimeters times 5 centimeters is 40 centimeters squared. So yeah, that makes sense. That answer makes sense. And I should always check to make sure my answer makes sense. Now we're going to use kind of that same idea again to find missing side lengths, where now I have, different variables and things. I have an area. Now I have a base. So let me take area equals base times height, and let me plug in what I know. So my area is 14 x to the 5th y to the 7th. The base is 2x squared y squared. And I'm looking for the height, right? So to find the height, I have to multiply 2x squared y squared times the height. So to solve for h, I would divide both sides by 2x squared y squared. Now these cancel out because they're exactly the same. And let me use my rules of exponents to kind of reduce this left-hand side. So 14 divided by 2, and I always start with like my fraction bar. Remember this? This is division. 14 divided by 2 is 7. That goes on the top. Now let me look at each of the pieces with same bases. So x to the 5th and x squared. They have the same base, right? So I subtract the exponents. 5 minus 2 is 3, but the 5 was bigger, so the x to the 3rd stays on the top. And now the next same base is the y's here. So 7 minus 2 is 5. So the y to the 5th, again, stays on the top. I don't have anything left on the bottom, so I can kind of put a 1 there. But then when we have the 1 on the bottom, or the denominator of a fraction, I don't really need it. So I'm going to simplify this one step further and just make this 7x cubed y to the 5th, right? But 7x cubed y to the 5th units. Same as kind of before. We don't know if this is inches or centimeters or whatever, feet or whatever. Now let's make sense, or let's check our answer to make sure that this makes sense. Sorry. So I should be able to multiply my two sides together, the one that I found, so 7x cubed y to the fifth, and the one that was given to me, 2x squared y squared, and I should get that area. So 7 times 2 is 14. X to the third times x squared is x to the fifth, and then y to the fifth times y squared is y to the seventh. These match up, right? So that tells me that I got the right answer. All right, so now you're gonna try this one on your own. So you're gonna find the missing side length. So you're given the area is 36, a to the 6th, b to the 10th. You're given one side is 9a cubed, b squared. Pause the video, take a minute, find that missing side length. And then when you unpause, you can check your work. All right, welcome back. Hopefully you were able to go through this, setting up your little equation and dividing, and your answer here, this base should have been 4a cubed b to the 8th units. And remember, you can always check your answer by multiplying this side that we found with this one, and you should get back to that area. All right, that is all I have for you guys today. Check Schoology to make sure that you finish everything and complete everything, turn it in on time. Thanks for watching. Have a great day.